Okay, so hi, good evening, everyone. I will be talking to you about SDR, which is software defined radio. The title of my LND session is SDR 101. We would be covering introduction to radio communication, which is extremely important to explain what actually is a software-defined radio. Then I would be explaining how does a software-defined radio actually really work. And I would be covering SDR hardware and tools, which some of the basic tools which I have discovered, and I think you need to get started with SDR. Then I would cover some of my demonstrations, and I would finally be ending with like a small note on how SDR is used in security. So coming to the first topic, introduction to radio communication. We already know what radio communication is, but just for the sake of continuity, SDR and radio, I'll tell you that radio waves are the electronic waves in the EM spectrum, lying between the range of 30 hertz to 300 gigahertz. These are the waves which are used in telecommunication, and it is possible through receivers and transmitters. So starting with the transmitter has these many modules. As you can see, this is the basic diagram of a most basic receiver transmitter, which we must have studied in our physics classes. So this transmitter has a power supply, which basically provides the necessary electrical power to operate the transmitter. It then has an oscillator. Oscillator is what creates the alternating current at a frequency at which the transmitter will transmit the radio wave or the data. The oscillator then connects to a modulator. The modulator also has another source of input, which is the actual audio or video information which we would like to transmit. Which modulator then combines the oscillating wave and the audio or video information and directs the input towards an amplifier. Amplifier amplifies the modulated carrier wave in order to increase its power. The more powerful the amplifier, the more powerful the broadcast. Finally, it connects to an antenna which converts the amplified waves into which converts the amplified signal into radio waves. Now onto the receiver. Receiver has an antenna which captures as an antenna which captures the radio waves. Usually, antenna is basically a small length of wire, and when this wire is exposed to the radio waves, it due to the electromagnetic EMF, due to the electromagnetic laws, the waves induce a very small alternating current into that wire. Since it's a very small current, the antenna connects to an RF amplifier, which is a very sensitive amplifier and amplifies the very weak radio frequency which the antenna gets, which and then directs the input to the tuner. Tuner is nothing but a circuit which extracts the signal at a particular frequency from a mix of different frequencies. Since the antenna will probably get a lot of noise, tuner is what lets us identify a specific broadcast range or a bandwidth to listen into. Tuner then connects to a detector. Detector is responsible for separating the audio information from the carrier waves, since carrier waves are what carries our data. The detector then connects into an audio amplifier. This component's job is to amplify the weak signal which comes from the detector and amplify it so that you can actually hear it or maybe receive it if it's a video signal. So I've explained to you basics of receivers and transmitters. Let me cover some topics which are important for software-defined radio and radio. So we know that for any radio wave to transmit, we need first a data wave, and we first need a data wave, and then we need a local oscillator and the carrier wave. Local oscillator is what produces the carrier wave, which is then mixed with using mixer and then received or transmitted. Um, I'd also like to touch upon intermediate frequency and filters. What a filter really does is that say if your data wave is of the frequency of 150 kilohertz and your carrier wave is around 10.7 megahertz, then filter would let you listen to only your required data of 150 kilohertz, and which produces an intermediate frequency which is where we listen. This 150 kilohertz is the intermediate frequency, which covers most of our data, or 90% of our data, as we would see, as I would explain through the waterfall and the radio wave diagrams in my demonstrations. So now I'd also like to touch upon the modulation. Say this is our signal, this is our data which needs to be modulated. If we simply transmit this data, it would not get transmitted properly, as this is a very weak signal and noise would easily garble our message. Hence we need a carrier wave in which we encode our signal and data and then transmit it, so that people on the receiving end can actually get your signal, right? So there are two ways of modulation: amplitude modulation and frequency modulation. In amplitude modulation, based on the data, your amplitude changes. Notice the curve, notice the upper crest here, and notice the upper crest here. In the frequency modulation, based on the data, your frequency changes. Notice the upper crest here, and the higher frequency here, and the lower crest here, and the lower frequency here. Now coming towards explaining what actually is a software-defined radio, right? So with the emergence of digital technology and wireless communication, SDR found itself to be at the center of these two technologies. Basically, SDR is the best combination of wireless and digital progresses in technology. SDR is nothing but the implementation of hardware components into software. So components which traditionally would have been in hardware are now converted through a software interface, and allow you and give you an interface to tune them using a software. So to actually work on a radio, you don't need very big components. It means that instead of turning and tuning all these different dials and tuners, as you can see here, this is a very old radio used in naval warships. Instead of turning all these different parameters and dials, like you see here, you can just do it on a computer system using a software interface like here, right? You could change your frequency, you can change your filter, which filter is what I showed you earlier. You can change your gain. You can change your frequency. Yeah, you can also change what bandwidth you want to listen to and whatnot. So what kind of hardware is actually implemented? So hardware which usually would have processed the signal has now been implemented into a software component. This would include filters, filters which I have explained to you earlier, amplifiers, modulators and demodulators, and many more. So this means that most modern radios that you use and interact with are actually software-defined radios. The FM radio app, or the FM radio in your phone is actually a software-defined radio. Satellites use SDR to communicate, and you can see these implementations all around you. But how does it really work? Honestly, the working of software-defined radio is extremely complicated. So the too long didn't read version would be it's just physics and maths. But if you want to, get into the details, it actually works on physics and complex mathematics. Complex mathematics deals with, as we all know, imaginary numbers. So this is how it actually works. If you really want to know how complex mathematics works, what happens is the sine waves, in fact, which are represented using a 2D diagram, are given a phase component. This phase component is due to the fact that you actually have an I signal and a Q signal. What actually why the emergence of SGR was the SGR emerged due to the fact that analog to digital converters were really expensive, and if you had to transmit or receive at higher frequencies, you would have to invest in higher and more expensive converters. So what they did was they decided to turn the IF signal, which is the intermediate frequency, to zero, so that ADC, the analog to digital converter, would have to listen to only the lowest of the frequency, which would be very cheap to produce. But what happened was half of the frequency was getting cut off, and was going into the negative. But to represent this, they used the phase component, and used I to represent that component. It's extremely complicated, and I would not spend more time, as like we already are very short in time. So basically, say in a normal SDR, you get the receiving frequency, and using mixers and these filters, you get an I signal and a Q signal, right? These I and Q signals go through the USB interface, and USB interface is what lets you change these I and Q components and tune what would tune with software implementations otherwise would which otherwise would have which for which otherwise you would need hardware to do, right? Is it complicated? Yes, it is complicated, but you don't need to worry, as we just work upon the other end of the SDR interface and don't need to worry about how SDR is implemented. So now I would now like to cover upon some basic software defined radio hardware. The first which I would like to cover is RTL SDR. RTL SDR is a very cheap USB dongle which is capable of receiving signals between 500 kilohertz to 1.75 gigahertz. It is a computer-based radio scanner used for receiving live radio signals in your area, and most of the software of the RTL SDR is community developed and provided free of charge. I would like to show you the RTL SDR which I have, which is on this slide here also. It looks like this with your antenna connected. I will show the implementation of it in my demonstration portion also. Now, how RTL SDR came to be was originally in Europe, TV tuners had this chipset called Realtek RT2832U. Researchers found that they could actually extract the raw I and Q signal from that chipset, and they could control the different parameters, because once you get the raw I and Q signal, you can develop the SDR implementations. And since this chipset allowed people to do that, they developed the RTL SDR implementation softwares and drivers on it. Now it's community developed, and anyone can view how it is done and develop tools for it. Just a second. Yeah, as you can see here, I had actually opened up my RTL SDR. This is the RTL2832U chipset. If you can see, it's actually written here, and and researchers could actually extract the I and Q data and work upon it. Next, I would like to cover HackRF. Like we have probably all heard of HackRF1. It's an open source hardware for software-defined radio projects and capable of transmission and reception of radio signals between the range of 1 megahertz to 6 gigahertz. What RTL SDR lagged in was that one could not actually transmit signals, but in HackRF1 you can receive and transmit both. You can do both with HackRF1, allowing you a lot more, allowing people and amateurs and enthusiasts a lot more things that they could do with it. Moreover, it also covers a wider range than your normal RTL SDR. Now, I would like to also cover upon some common software-defined radio tools. These include GNU Radio. GNU Radio is a software development kit that provides signal processing blocks to implement software radios. What this means is that you can basically tune each part of the radio as if it were real hardware, and then turn it into a flow graph which the SDR follows. This flow graph is what you see here, and it's based on Python. So basically, with these flow graphs, you actually create a Python program which the SDR hardware follows and runs. It is and provides a basic block for SDR development. So meaning, as you can all see here, you can actually set parameters here. You can set some basic arguments that say I would like the bandwidth to be 650 kilohertz, and then I would like the gain to be 30 decibels, and then I would want it to rotate the phase by this, and then I would also like to set up a UDP server to catch and listen to all the data. So this basically provides a basic building block for developing software-defined radio projects. Next is GQRX. GQRX is used for basic radio tuning and to get a rough overview of the bell curves and the bell curves and the transmissions around you. It is based on GNU radio and provides an interface to process the IQ data from the supported devices. Right. It also allows you to change the various parameters and tinker with them. Like you can see here, you can change the frequency at which you want to listen to. You can change the filter width. You can change a lot of different things, including gain. You can even record what you're listening to and then save the data, and then maybe reverse engineer what was being transmitted later. Next is Universal Radio Hacker. Universal Radio Hacker is like a complete suite for wireless data investigations. It allows you to easily demodulate the signal, and it also has automatic detection for encoding and modulation parameters to allow viewing of the raw data. Meaning, say you have captured some signal using GQRX or URH, which is the Universal Radio Hacker itself, then it can understand what modulation technique was used. It can understand what raw data was being sent, and then you can actually move on to decrypting or reverse engineering it. So all in all, it is used to capture, analyze, decrypt, and reverse engineer your radio communication packets, raw packets that is. Next, I would like to cover upon Dragon OS. Dragon OS is actually a complete suite, Lubuntu based suite of tools, and it's actually a virtual machine, and it provides all the dependencies and all the tools in it pre-installed. I would recommend that if anyone is starting out with SDR, I would recommend you to actually search up Dragon OS and install it, as sometimes, as many times, one GNU radio based tool does not work with the current update of GNU radio and whatnot. So there are a lot of dependency problems, and Dragon OS is what solves it very easily. To mention some more tools, there is Qt Radio, Calibrate HackRF, and Calibrate RTL Toolkit, and the RTL Driver Toolkit. All of these, which I'm sure you will come across as you start your SDR tinkering journey. Now the lecture is over. I would now like to.
Hi.
Yes, sir.
Yeah, this is Rahul.
Yes, sir.
These all SDR radio applications are based on Linux, right? Kali Linux.
Sir, there are many Windows implementations also.
Okay.
SDR target.
Have you tried AirSpy?
No, sir, I have not tried it since I have not tried AirSpy.
Okay, fine. Thanks.
Yes, sir. So now I would like to show you some of my demonstrations of what I have tried to find out and tinker with. So the first would be to basically, pardon me.
This demonstration you have done with the HackRF or your that USB device which was there?
Sir, I would be showing you demonstrations with both RTL SDR and HackRF.
Okay.
Yes, sir. So the first demo would be listening to radio FM. So I will be using my RTL SDR right here, and I will use GQRX to manually tune into 95.3 megahertz, which is where you can listen to Red FM. Okay, so I would be connecting this to my laptop. and I would be setting the antenna to a magnetic surface. I didn't have anything else, so I just set it here, and I'll keep it so that it stays upright. Um, Now, to make sure that my laptop has detected, I would just first run ls USB, and you can see that it detects my RTL USB module. As you can see, RTL 2838 DVPT here. Now I would run GQRX dash dash reset. You can run GQRX like that also, but since I have some configuration saved in it, I'm running it with dash dash reset. With this, with dash dash reset, you actually have to configure a device every time. So I open the device thing and I select my Realtek RTL 2838, and then I just click OK. As you can see, GQRX has opened. To start listening, you press the play button over here, and as you can see, it's just a lot of static noise. So unless you actually know where to tune into, you will be listening to a lot of static noises. I will just turn this to 0, and now I will turn this to 9, then 3.5. And now I will turn the mode in from AM to wide FM, and I will increase the gain. And like if you can hear my audio, you can actually listen to the radio. Could anyone tell me if it's actually audible?
Yeah, it's pretty much audible. We can listen to the advertisement there. Good.
Yeah. Okay. So this is the first basic implementation of SDR.
Okay, one more thing.
Yes.
Have you closed it?
No, I'm not.
Okay. Do you know what is the meaning of AGC there, which is on medium?
Sir, no, I am not aware of that. I'm not aware with all of these, but I'm just using the default configuration. I'm not aware of AGC.
Okay. We'll
Yes.
talk about later, okay? I have something more to share with you then.
Yes, sir. Sure.
Okay.
Uh,
Go ahead.
going to the next demo, we will use web SDR to listen to communications happening in the United States. So I'll just close this for a moment, and
The communication which is happening in United States, but where? I hope it's not their military.
no, sir, no, sir, nothing illegal is happening here. Is happening here. It's just
That we will know when someone will arrest you soon.
no, sir, that nothing illegal is happening. So let me tell you about Web SDR before we start. So Web SDR is what is when say I have a very big SDR receiver. I can set it up in my backyard, or I can set it up in my place, and then I can give the SDR implementation of it online for anyone to use. So this here is a SDR receiver 6 miles south of Half Moon Bay, California, USA. Okay, this facility is maintained by this particular person, and he has given the control to anyone who wishes to listen to this. Okay, so basically, I'm getting like in GQRX, you can see the waterfall here, and I can tune into any frequency which I want to. I'll just press this button, Chrome Audio Start, and I'll tune into this. If you're able to hear, there's actually people talking.
I called 16 Carter. She drove 16 towards the Thomas Hill.
Could anyone confirm if the audio is?
Yeah, we can see that. So, what role your capture card is playing in this?
Pardon, sir?
What role is your SDR card playing in this activity?
Yeah, so sorry, I should have told that earlier. Right now, my SDR card is not doing anything. The SDR card implemented by that person in California, that I am actually accessing his SDR card using a web interface. Sorry, I just reduced it. Yes. So I'm actually accessing or using the SDR card implemented in this place using a web interface. And to able to see all the WebSDR implementations which people have allowed, you have to just go to websdr.org. And here it also tells you that this is a SDR receiver connected to the internet, allowing many users to listen and tune simultaneously. This makes it possible that all listeners tune independently and thus listen to different signals. This is also a very key difference between normal radio and SDR, is that with SDR, different people can listen to different signals and different frequencies. Whereas on actually normal radio, this would not be possible as the hardware is what is being changed. Here, the radio signal is what is being changed as you listen to it. So here you can see there are around 181 servers active. You can also create your own server. And in fact, if I wanted, I could create my own server using my SDR and implement it over here. Sir, if it's okay, I'd like to continue to the next portion.
Yeah, if in case anyone having any question.
Yes. Now I would like to show you how to use like the Universal Radio Hacker to capture and understand a car key fob signal. So for this again, I will just type URH. And the Universal Radio Hacker opens up over here. To confirm again, I'd like to show that my RTL SDR is currently connected and listening whenever I want to tune to it. So for this, I will actually be using this car key fob. Like I'm pretty sure we are all aware of these car keys, which when you press this button, like unlock or unlock, it opens the car using
Which car is this? Which car's key is this? By the way, any model number?
This is Skoda. This is actually not mine. This is my friend's because we don't have a car which has this. So I borrowed my friend's. This is a Skoda car.
And what special is this in the key? Is this a old technology? Because I've tried the same thing. The only thing I ended up is doing a DDoS attack on the doors.
Yes, sir. So I'll explain the entire thing. I did research and dive into this. Right now, I'll just like to show you. I'll just like to talk about that car key fobs, the remote control cars, and those small helicopters and remote control cars, etc. And remote controls in general, they work on the frequency of 433 megahertz.
Yeah.
Okay. So Universal Radio Hacker starts to listen on this. So to actually show you, I will just open a file and then I'd say Spectrum Analyzer.
So I'm interrupting you. So I'm curious to know because I've done the same thing, but I landed up without a success. So once you're able to capture the keystroke, right?
Yes, sir.
Okay. Have you send it as a repeater to the car to check?
Sir, so as of now, I can't. I'm using an article SDR which does not repeat. Number two, you can actually repeat it, but as I'll explain, like if it's okay with you, I'll explain how the car key fobs really work and how they've changed so that to avoid replay attacks.
Okay. I'm good.
Yes, sir. Yes, I'll explain to you. That is part of my demonstration. So I'll set the device over here to RTL SDR. I'll set the device identifier to refresh so that it detects my RTL SDR. This is the basic frequency which it's listening to, and I'll just say start. Now it's just listening to this. If I press this once, you can see there's a lot of noise generated here. To tune into the perfect frequency, I'll go to this. I'll click here, and then I'll press it here again. And as you can see, there's a lot of noise generated here again. To finally tune it again, I'll click on it here. And then I'll press this again. And as you can see, this is the bell curve. This is where the signal is being transmitted. In the waterfall display too, this is we can see that this is when the signal is the strongest. Okay, so the frequency is 434.39, etc., etc. So I'll press this once more just to be sure, and then I'll stop it and I'll clear it. Now Universal Radio Hacker has stored what frequency I want to listen on. Now I'll go to record signal. I'll select RTL SDR, it's already selected here. I'll refresh the device identifier and then I'll start. Now, if I press lock, unlock, and stop. So I have actually captured the wireless signal which is being sent when I press lock, and when I send unlock and unlock. I can save it, and then I can clear and I can close it. Now, now what we have done right now, we've analyzed the spectrum now, and we have captured the signal. Now, as Rahul sir was mentioning, that now it's very easy. Just plug your hack RF, go to the car, and then replay it. But how car keys and cars actually work now is that they actually have a key algorithmic key shared between them. So whenever I press unlock here and the car unlocks, they both increment a counter in their algorithm by 1, and then they match their algorithm, and then they match the output from that algorithm. If the output is the same, then they unlock it. So it means that, say, if I captured this lock and I try to replay it, the car key has no fob to connect. Sorry, the car has no fob to connect to and increment the algorithm by 1. So it will actually not unlock. That is why, Rahul sir, you were not able to unlock the car. You could only just DDoS. So just for demonstration's sake, I will also open the file which I have saved, and I will go full screen. So this is the data which I had captured. If I really zoom into it, I can actually see the data wave which is being transmitted here. Okay, and the data wave which is being transmitted here, and using the URH, I can like auto detect the parameters. I can analyze them. I can generate say I can change the signal to what I want to, since I have the raw data over here. Okay, I can select portions of the data which I want, and then I can save these portions here. Say I just want this portion here. I can select it, and then I can save the signal separately. Okay, coming back to like how the car key security really works. So like around say 7-8 years ago, they actually did start implementing this shared algorithmic key. So when I press lock, the car key, this sends the signal to the car. The car receives the signal. It increments its algorithm by 1, and then it checks back with the car key fob to see what the output of the algorithm is. Since we have just captured the signal, we actually don't know what the key is or what the algorithm is, we don't really know how they work. So when this method first started was the counter could only increase up to 256. So so if say someone left this for 5 minutes, I could just press this 256 times so that I could see the counter go 256, and then I could record it. And then when I go up to the car, I can just play each of those 256 signals for it to unlock. But now they've incremented it to more than 65,000, if I'm not wrong. Moreover, now how this car key security implementation can be overcome is, what they do is, say you are near your car and you press unlock. It using hack RF, it sends a jamming signal and it captures your signal. Okay, which causes it's basically a DDoS attack. It sends a jamming signal and saves the signal which the car key fob sends. Then what it does is the user, since he wants to unlock the car, he will press unlock again. Hack RF1 jams the signal again, and it sends the signal which it captured earlier. Okay, so what happens is it connects with the key with the older increment, and you actually have the current increment which you can go and play. It's a really interesting thing, and I will link it up in my PDF when I share my resources. Coming to the fourth demonstration, I would like to show you how to use your phone with RTL SDR. That is how you can connect the RTL SDR with your phone and do what I showed you earlier with your phone, right? To do so, I think I would like to show this demonstration in the last, because I would have to share my phone screen. It would take time, and I think we are running out of time. Next, I'd like to show you how to sniff GSM and cellular data. I won't show you how to get all the juicy details, but I'll just show you how to study about GSM technology and how to capture or sniff it. Okay.
Quick question. Can we see the juicy information technically?
Sir, for that you would actually have to have the key which is used to encrypt the juicy information. And for the key, I had not gone that far into it, since I am also working on this on my end semester project, and that's a whole different ball game. So yes, technically you can see the juicy information, but you need a key for it. That key can either be provided by the cellular provider, or you have to extract one.
So that's not that easy. Yeah.
Yes, sir, it's not that easy, but it's easy for governments to do, because cellular.
If you do that, that's highly illegal to do that, because that becomes the decipher for your entire cellular communication.
Exactly, sir, exactly.
You should not do that. Okay.
Yes, yes, sure, I won't do that.
Okay. Thanks.
So if we want to listen on GSM signals, we have to first research about what signal GSM actually is in. I have actually researched it, and the range of GSM is it is actually upwards of 850 megahertz in India. Okay, I will now first connect my HackRF to my system. To show so, I first to connect your HackRF properly. Sometimes you may need to run sudo modprobe HackRF. What modprobe does is it actually adds a module to the kernel. So I have actually added the HackRF module to my kernel. And if I press ls, if I run HackRF_info, which gives you the info for your HackRF device, you can see that I get that my device is working properly. Now to do so, I'm going to switch over to Dragon OS, and I'm going to start this right now. Okay, so I hope everyone can see my Dragon OS screen.
Yes.
Okay, cool. So first of all, what I'll do is I'll connect my HackRF to this virtual machine. I'll click on this USB button and connect it. It disconnects from the host and connects it to the virtual machine. Now I'll do the same. I'll run HackRF_info to see if it's being detected, and yes, it is being detected. Okay, so first I'll stop all, since I'll be showing how the GSM data looks. I'll first disconnect it from the network using NMCLI networking off. Otherwise, you get to see a lot of unnecessary network data too. Now, what I'll do is I'll go into the place where I've installed the IMSI sniffer. And then I'll run that particular script. Okay, this will run in the background. Now to actually see where the data is, because how GSM works is there are specific downlink and uplink channels for each GSM base station. So you actually have to find that particular downlink and then listen to it, because it can't just broadcast everywhere. Okay, for this, I am actually using GQRX and trying to find specific bell curves where the downlink and the uplink channel is. Right, like say here, there's a particular rise here. It means something is being transmitted, although I'm sure it's not GSM because the bell curve is much higher than. So I'll slowly increase the frequency which I'm listening to. And I'll see that there's a lot of noise here, which makes sense because GSM is being, which may be because other communications are happening. I'll increase it further. What we actually need to do is we need to find a bell curve, a very strong and sharp bell curve. I increase it even further, and I think this is something which looks interesting. If I increase it to 949 and tune it even further, you can notice that this is a very strong bell curve and this is a pulsating bell curve, which means this is the place where GSM communication is happening. This is a GSM downlink for the base station to communicate with the cell phone, and this is a channel hopping frequency. So I think we've identified that usually it's around 949.3. I can actually start listening. So as I've explained to you that GQRX is useful to see and tune the bell curves as we want. Just a second. Okay, so now I would like to start GRGSM. What GRGSM suite of tools is, it's of course it's based on GNU radio, and what I showed you earlier was the GNU radio implementation of GRGSM only. So it basically listens to all the frequency and it tries to capture the actually tries to capture the GSM data. Before we do this, I would also like to start Wireshark so that I could show you the data being captured. I'll just run it. And switching over to LiveMon. Since it was around 949, since the frequency was upwards of 949, I'll slowly increase it. Before I see a bell curve here. I think we actually see a bell curve. GSM is not very good at showing you the bell curves. So you have to use GQRX to identify and then tune to the frequency. As you can see, I'm getting some random data. If I tune it even further, I should be able to listen to it properly. As you can see, yeah. So now we are successfully capturing GSM data. This is how it looks like. Switching over to Wireshark, we can see that this is indeed GSM data as Wireshark automatically detects what is being transmitted. Opening a specific packet by double clicking on it, you can see the different headers and the information. Although you will not be able to see, as Rahul Saraj, you can't see the juicy data because it is encrypted. So
Siddharth, can you do one thing? Can you go to the
yes,
protocol filters and type GSM there in
yes.
Wireshark?
Which one would you like me to switch to? Because this is GSM tap, which is here.
Okay, anything which makes sense to you, because I'm on my
Yes, this is
mobile, I
GSM.
can't see that clearly.
Oh, acha, okay. Do you want me to zoom in?
Yeah, little bit. It's okay. So you can specify the GSM packets also if you are pretty much suspicious that what's going on.
Yes,
You
sir.
can see now.
Yes, sir.
So yeah, thanks.
Yes, sir. So, if it's possible, I'd like to tune it even further. Uh, yes. So, as you can see, you can actually save this capture file, and you can see what GSM data is being transmitted around you. This particular script doesn't seem to be working, so I'll just refresh and play it again. What this does is it actually sees the packets which are being transmitted here, and it tries to decrypt. It tries to basically whatever headers you see here. This simple script, it identifies the important headers and it shows you what each of these headers mean. So this is basically the basic information. You can see the brand, the operator, the cell ID, the timestamp of this particular person. I won't run this longer. Because I would not like I would not like the MC data of people around me to be publicly available. So this is I would now like to close Wireshark, and I'm done with this particular demonstration. So I would now like to end with SDR and security. Like we've seen these demonstrations. As I've showed you all of my demonstrations, like you can there's a like SDR can be used for enthusiasts who are interested in how radio works, because honestly, wireless communication and wireless security to me is very interesting, because it's just around you. Your data is passing through you and around you, and if you have the proper tools, you can actually see what is happening around you. And so and so SDR as a technology and as a tool in security is extremely interesting to me, as we've seen that and if I work, or if I am malicious enough for me to even look and decrypt GSM packets. And for people with more research interest, people have cracked 3G, 4G, and even 5G. There are a couple of researchers who are working on 5G security, and you can actually, if you spend around $500, you can actually decrypt and catch 4G LTE data which is being sent. So with this note, although I have skipped on one demonstration, which is using SDR and use in a phone, but I think I'd like to close this as as my time is over right now. So thank you.